Thank you so much for these organizers for inviting me. Yeah, I'm really happy to talk. So what I'm going to talk about today is going to be some. I'll have to repeat some of the stuff Kevin and Victor were talking about before, but I'll talk about this in more detail and maybe give some new perspective on this thing. So was told, the topic of my talk is representations of general linear group in the Verlinde P. And I'll start with repeating the result we heard from Kevin. So for me here, I will be working over some algebraically closed field of characteristic P, some prime characteristic. And so Verlinde P will be the category, as before, the semi-simplifications of representations of this cyclic group of order P. But another perspective on this will be that I want to also think about this category as the semi-simplification of the category of tilting modules over SL2. So I think, Victor proved that it was the same. So that's you get the same category applying the semi-simplification construction to tilting modules over SL2. And so the simple objects of this category, there are finitely many. It's a fusion tensor category, symmetric fusion category. So it has P-1 objects. And from this perspective, you can think about them as things that come from Jordan blocks of corresponding sizes. And from this perspective, you can think about them as this tilting modules over SL2 that are simultaneously Weyl modules and simultaneously simple modules over SL2. So they go from dimension 1 up to P-1. And L1 here is a monoidal unit. And so dimension of Li is I, the categorical dimension. And moreover, so if you want to take the tensor product of two such things, you would need to use some modified Clebsch-Gordon rule. And a lot of properties come from this picture of SL2. For example, L2, so this two-dimensional simple object, it's sort of the generating object for our category, and every other thing is just the symmetric comes from symmetric powers of L2. So it's if you take K symmetric power, we get K plus first object. Okay, another thing about this category, I guess just maybe I will need to use is, as was told, if I only look at L1 and LP-1, then I'll get a subcategory of supervector spaces in characteristic P. Okay, and so this nice theorem by Kevin, Pavel, and Victor. Let me repeat one more time, although we heard it 2 times already today, but still. So it tells that Verlinde P is an interesting category because it serves as sort of as a source of fiber functor in characteristic P for many nice categories. So for any pre-Tannakian category Frobenius exact of moderate growth. So in particular, any semi-simple category of moderate growth is such. So it admits essentially unique tensor functor F from C to Verlinde P. And so let me illustrate some examples of those such fiber functors and also give you some examples of other semi-simple tensor categories in characteristic P. So what one can do is...
and maybe we should say that pre-Tannakian means the same as Kevin called the just tensor case.
Yes, yes. So in Kevin's notation, it was just tensor. So we can try to imitate this construction over here and look at the category of tilting modules of some reductive group G. And so if P is large enough compared to G, so if the Coxeter number is less than P, then, so we'll call this, the semi-simplification of this, we'll call Verlinde P of G. And it's going to be some semi-simple tensor category. And we can also classify which kind of objects survive after the semi-simplification condition. And the answer is that you also get some while modules in this chamber, where the while modules are also simple modules, and those are given by some highest weights lambda, with the condition that lambda plus rho paired with this longest root theta is less than P. So just some combinatorial condition like this, when you can describe this category, and moreover...
I think maybe theta check, yeah? Should it be theta check?
Well, it depends on, yeah, so maybe with these brackets it should be theta check. Yeah. Okay, so in this category it meets a fiber functor to Verlinde P, and there is a pretty straightforward description of this fiber functor in this situation. So,
and is it also less than or equal to P rather than less than P? So inner product.
I think
because
it's
you have a rho?
strictly less than P.
Wait, isn't P the Steinberg?
Like PSL2, like this would be lambda plus 1.
Wait, maybe I'm... So I want to say that it's not... Yeah, okay, lambda plus 1.
Lambda is a weight. Okay, then it's correct. Okay, thank you.
Yeah, it's a weight, it's not a dimension. Yes. We can describe the fiber functor. So it turns out that you can, so let me write it as a verb P of SL2. And so it turns out that you can sort of understand this functor upstairs before semi-simplification, and it's going to be the restriction to the principal SL2, and it will, well, tiltings will go to tiltings, negligible morphisms to negligible morphisms, and you can push it down to semi-simplification. So it's induced from restriction to principal SL2. Yes?
Do you get any such functors from other types of restrictions?
No.
Just this principal SL2.
Well, maybe, well, so as we know, all fiber functors are, fiber functor is unique up to isomorphism. So if you have some non-principal nilpotent, then you will get something different, and you cannot get this. But yeah, I think you really need this condition.
It won't preserve. It will not map negligible. It will still map.
Tilting,
but will not map negligible morphisms.
Yeah, so we want this. Okay, so yeah, that's our fiber functor.
So sorry, what is the principal SL2?
So you take a nilpotent in the open orbit, and you just continue it to some SL2 subgroup. Okay, so so Kevin briefly mentioned the reconstruction theorem we can do from this, so I want to spend a bit more time on this. So when we have a tensor functor between two categories, then we can reconstruct the source category from representations of some group scheme in the target category. So that's what I want to talk about. So maybe I'll call this introduction to Verlinde P as the first part of my talk. And so the second part will be discussion of representations of affine group schemes and just affine group schemes in general. So the definition is, so the category of affine, so here I'm going to start with some symmetric tensor category C, and affine group schemes in C is just the opposite of the category of commutative int Hopf algebras in int completion of C. Right, so I'm just thinking about the corresponding rings of functions on groups. And so when I talk about a representation of G, so here on this side it will be the corresponding algebra, I'll call it K of G, and so representations of G is just, so in C, is comodules over K of G, also in C. Okay, so now, so that was the first definition, and as we heard before, any symmetric tensor category has some canonical affine group scheme in it called the fundamental group of this category. So I'll give a quick definition of this. So the fundamental group scheme of C, it's often denoted by pi1 of C, but I for sure will write it as just pi of C. It's a fundamental group of C. So, so here I just want to give another perspective of how to work with affine group schemes. So instead of just looking at the corresponding Hopf algebra, one might also define the functor of points for G.
So there was a request.
Oh, yeah. Okay, let me use that word over there. So if we start with any group scheme G and any int, so any commutative algebra in int completion of C, then we can define the functor of points on G. It's just homomorphisms of commutative algebras from K of G to A, right? And so not every sort of functor like this is can be presented by some actual algebra, Hopf algebra, but we will still, some of them are presentable, but I'm only going to define what is the functor of points for fundamental group of C. There is some coherent construction that allows you to define the Hopf algebra, but I think it's still nice to look at the functor of points. So before, Kevin had this notation that you can take tensor automorphisms so in this particular case, it will be identity functor on C, and you want to turn it into a functor of points. And so the way you do this you just, to each A, you assign the tensor automorphisms of some functor, let me call it phi A. It's a functor from C to A modules in C that sends every object to sort of the free A module on X. And you can take tensor automorphisms of this functor.
Maybe
yeah, so I want to keep this definition on board for a while. We'll use it later. So what's nice about the fundamental group? Well, the first fact that we want to use about it is that it has the action. So pi C acts on every object of C. And so if you were working with just regular algebraic group schemes, the way you would see this, so some action of some functor of points on an object X would be the action for each A of this group, A points of this group on A tensor X. And you can see that this automatically holds because of the definition of pi of C. Okay, so it acts on every object, and we have the Tannakian reconstruction. So theorem we're doing. So let's start with some tensor functor between two categories, symmetric tensor functor from one symmetric tensor category to another. Then it's pretty easy to show that this functor induces the map of affine group schemes in D from pi of D to f of pi of C. Let's call this map epsilon. And then one can consider representations of this f of pi of C inside D. Right, so we can consider some representations of this group scheme. Now f of pi of C is a group scheme in D.
And this f of pi of C is the same thing as the tensor automorphisms of f.
Yes, you can show that that's the same thing. And so, and with one restriction is that, so when you restrict this representation of this group to pi of D over using epsilon, you want to get this canonical action of pi of D. So that's what this category is about, this category with epsilon. And this reconstruction gives you C back.
So this is what Kevin meant when he said that any category which maps to D is a representation of group scheme in D, but this is a slight lie, and then he didn't explain what the lie was, so that epsilon needs to be put in.
Okay.
So sorry, were you saying that group scheme is not representable, or you're not worried that it's
It is representable by some coherent construction. I just didn't want to mention it. It's just easier. Some facts are seen from the functor of points. Okay, so now using combining this reconstruction theorem with the theorem by Kevin, Pavel, and Victor, we get that any pre-Tannakian Frobenius exact of moderate growth symmetric tensor category, well, we know that it admits fiber functor to Verlinde P. So in particular, we get that it is a representation equivalent to representations in Verlinde P of some group scheme on Verlinde P, like this, together with a map epsilon from the fundamental group. And so this was the motivational part of my talk. And now the second part will be actually discussing how the representation categories look like for the easiest group scheme with the map from pi of Verlinde P. It's the general linear group.
So, what is rep P, f of pi of P of comma epsilon? Like those are representations?
Representations, so that when you restrict via epsilon, you get the canonical action of pi of D. So pi of D comes with an action on every object. Okay, so so that's part 3 of my talk. So let's try and start just classifying representations of some group schemes in Verlinde P. And let's start with the easiest one. It's general linear group. So you can know, so it's actually some group scheme that you can define in any symmetric tensor category in any object X. You can define the group scheme GL of X. And I'm going to So let's C be a symmetric tensor category, X an object of C. And so GL of X, again, you can define the Hopf algebra of functions, but let me tell you what the functor of points is. So the functor of points is actually homomorphisms in the category of A modules. Sorry, maybe not homomorphisms. Let me write it as automorphisms in the category of A modules of this sort of free module on X. Something that you would get for usual GLX, right, for X vector space. So you can see now that since it's automorphisms of A tensor X, just by staring at this definition, you can see that every such scheme, it comes with natural homomorphism. Group scheme comes with a natural homomorphism from pi of C. Right, because there is this automorphism of A tensor X that sort of commutes with all morphisms between objects, sort of the way it was defined. So A points of pi of C were some automorphisms of A tensor X for each X. And so in particular, you can restrict it to some particular X. Okay, so that's the easiest example of a group scheme coming to this homomorphism from the fundamental group. And so let's study those in Verlinde P. So for this, I want to give a small remark about some results of Siedert and contention. A lot of what I'm going to talk about was done by Siedert. So here, by Siedert. So if we want to study representations of group schemes in Verlinde P, then, well, it's not that easy of an object, some Hopf algebras, in-Hopf algebras, but there are some techniques that are very similar to the techniques used when studying representations of supergroups. And so instead of looking at some group G, what we can do, we can, so to any group scheme, we can assign the Lie algebra G, so it's Lie of G, so it's defined in the same way as before. You can look at, so inside K of G, there is an augmentation ideal. You can look at this augmentation ideal modulo this ideal squared and take the dual, and that's going to be the Lie algebra of G. And so this is a more easily understandable object. And another thing you can assign to a group scheme G is the so-called even part of G. Let me explain what it is. So I here is the, let me call this I1, the augmentation ideal. But you can look at another ideal in K of G, let me maybe call it J, just to distinguish it from the one before. So in your Verlinde P, you have finitely many simple objects, and L1 is the monoidal unit. So let's consider the ideal generated by all sub-objects in K of G that are not isomorphic to monoidal unit. Not isomorphic to L1. Well, if we were in the setting of supergroup schemes, this would give me the ideal generated by the odd elements in K of G. So why is it a valid thing to consider here? Because the Verlinde category, it's very similar to the category of supervector spaces in some regards. So one of such regards is that every object other than monoidal union is nilpotent. So you can take the P minus K plus first symmetric power of Lk, and you get 0 for any K greater than 1. So those objects eventually, so when you work with symmetric algebras, finitely generated, then they all come from as quotients of some symmetric algebras. And so in particular in K of G, which is a, so here let me assume, sorry, I need this assumption, assume K of G is finitely generated. So it's a quotient of the symmetric algebra on some object in Verlinde P rather than in completion of Verlinde P. Then, so every object, subobject not isomorphic to the monoidal unit is nilpotent. So if I look at K of G modulo J, then on one hand, this is a purely even algebra, so it just consists of some copies of monoidal units. So it's like some vector space tensor monoidal unit. So it's a regular algebra on one hand. And on the other hand, so the actual K of G, maybe let me write it like this. So K of G is a nilpotent thickening. Of K of G modulo J. So J is a nilpotent. J is ideally generated by some nilpotent element. So yeah, so those are two kind of things we can assign to a group scheme. And the theorem is that this gives you an equivalence of categories. So finitely generated, well, group schemes of finite type with the finitely generated algebra functions. So this category is equivalent to the category of so-called Harish-Chandra pairs. Where on one hand you get a usual algebraic group scheme in vector spaces and the Lie algebra object in Verlinde P with some condition that the even part of this Lie algebra is precisely the Lie algebra of the even group. Yeah.
The even part is represented by.
Yes, sorry. I did not write it. You're right. So K of G even is K of G quotient by J. Thank you. Yes. Okay, so that's how we are going to think about group schemes in Verlinde P. We'll be thinking about an even group and a Lie algebra object.
Sorry, if I can bother you about this thing you kind of moved on from. So in the supergroup case, I want to say like this is just choosing order 2 elements inside of when I fix some different A, and I look at the values of epsilon. Yeah. Is that what it's doing?
Sorry,
so like in the supergroup case, maybe I'm confused. I guess in this case, I'm thinking D is supervect.
Yeah.
Maybe just a little bit too complicated for me to be asking right now.
No, so fundamental group of supervect is Z mod.
Z mod to Z, yeah.
Yeah, so is it just...
You'll get the, so X is going to be some of some even part and odd part, and this will be the embedding of like 1, so it's going to be 1 on an even part and -1 on the odd part, something like this.
Okay. Okay.
Z2, the supervector spaces, the fundamental group is Z2, right?
Yes.
Exactly.
It's just going to act as a parity element. In this case.
Yeah, question.
Yes.
So the content of the theorem is what representations of G?
Oh, sorry.
Representations of the.
This is a very poorly written down theorem. Sorry. Let me try again. So first of all, we get an equivalence of categories of affine group schemes, Verlinde P of finite type, equivalent to Harish-Chandra pairs, and in particular, you get that representations of any affine group scheme G as a category is equivalent to representations of G even and representations of, well, it's some sort of data where you get a representation of an even group. It gives you a representation of an even Lie algebra. And you also get a representation of a Lie algebra object, and you want restriction to the even part to be
As in the classical setting.
Yes.
Yes. So the same, absolutely the same picture.
And so, like following up on the question about the parity, does that mean that in the case of supervector spaces, you'll have like only purely even representations or something like that?
Yes. You're not allowed a parity change, sort of. Yeah. Okay. So what is then GL of things? So we start with some object X in Verlinde P, and let me choose some decomposition of X into the sum of irreducibles, together with some ordering of those irreducibles. That's important. So GL of X, well, first of all, we already defined what it is in terms of functor of points, but let's define it in terms of Harris-Chandra pairs. So the even part of this will be the group that only permutes like some components of the same components, like isomorphic components. So it's going to be the product of GL and I's. And the Lie algebra is what you expect. It's X tensor X dual, and it's sort of like this matrix thing where you get Li tensor Lj dual. You kind of sum up over all things that are present. Okay, so what Cedar did then, trying to classify representations of this group, is some sort of highest weight theory. So let me give you a quick recap of his result. So what you can do is you can consider some sort of analog of a torus inside GL of X. So this torus is more of a Levi subgroup. So it's going to be the thing that is sort of the product of GL of Li to the power ni. And so as a Harris-Chandra pair, so let me maybe introduce the constant n, which is the sum of all ni's, just the number of indecomposable components in X. So as a Harris-Chandra pair, this is the corresponding even group here will be precisely the n-dimensional torus. And the Lie algebra, the Lie subalgebra here, it's just this thing that sits on the diagonal. Okay?
Yes, Sasha, may I make a quick comment?
Of course.
So I just want to introduce a mental picture that you should be keeping in mind if you're not used to this kind of stuff. So suppose you have complex numbers, a finite dimensional representation of SL2 into n-dimensional. So you have a homomorphism from SL2 to GLN. And then I give you a task of developing representation theory of GLN where you are not allowed to do anything that is not equivariant with respect to this SL2. So in particular, you cannot choose a Borel subgroup if this representation of SL2 is non-trivial. You can only choose parabolic subgroups, but if SL2, for example, you have a principal SL2, then you cannot even choose a parabolic subgroup. So, you have to recover the main results, and the same for other Lie algebras. So recover main results of Lie theory, working equivariantly with respect to some SL2 sum. And so this is a characteristic P version of that.
Yes, thank you. Yeah, so yeah, so some intuition behind this is really you think about this sort of SL2 equivariantly, and you think about those LIs as some representations that appear.
This picture is obtained by semi-simplifying exactly the picture I give at characteristic.
Okay, so yeah, so we can introduce this sort of torus, and you can introduce some analog of the Borel subgroup. And
so that this torus is non-abelian, like you said correctly, it's more like a Levy, but it is a poor man's torus because we cannot really choose it.
Yeah, beggars not choose it. Yeah. So okay, so Borel subgroup will correspond here to the choice of Borel in each of the GL and I's, and some choice of ordering of those elements, right? So we want to sort of choose something upper triangular, and this choice corresponds to the ordering of indecomposable components that we have. So we actually get barrels. We can get different choices of barrels corresponding to those ordering of Li. So W here will be an element of Sn, and this will be some choice of barrels in the even part, and here it's going to be the direct sum of Li tensor. Maybe let me pick some ordering, right? So it's Li1 plus and so on plus Lin, and then it's going to be Ik, Ij with k less than or equals than j, something like this, right? You know, so it's just a choice of upper triangle of things. It's a choice of so as in the classical case, to choose a barrel, you need to choose the ordering of vectors, of basis vectors. So you sort of do a thing like this, and you get different barrels for each ordering. And now here I did not write. So here you would also get different barrels depending on what is the relative ordering of the copy of each Lk in here. And I can just fix the even barrels. So let me fix some choice, standard choice of usual barrel. And then this W should preserve the ordering of elements of the same type. I'm sorry, this is some technical details, but we could. So different choices of barrels up to fixing the even barrel will correspond to coset representatives in Sn, quotient by Sni1 times with Snp minus 1 of minimal length representatives. Okay, so this is not that important. What's important is that there are different choices of barrel, but for now, we could fix any one of them. And what then one can do is start with a representation of a torus, inflate it to representation of barrel, and do some sort of parabolic induction here. So let me.
And this fact that there are many barrels is very familiar from the theory of supergroups.
Yes, so that's something you might have seen in supergroup theory. So you get different barrels, and you don't get, so this Sn here, it's not an honest while group. It's something that does not act here. What we get is those honest while groups or even groups, so those SNIs, but we quotient out by them, we fix some choice of barrels in the even part, and then we get some barrels. They are different, they are not conjugate to each other, and so there is something to work with here. So that's some sort of a mystery here how they interact with each other. But for now, let's fix some barrel, and then we can do this highest weight theory. It's also due to Siddharth, so I'm not going to erase his name here. So fix. And also, so maybe just a comment on this epsilon here. So those GL of Li's, they come from with a homomorphism from the fundamental group, and a homomorphism from the fundamental group to the torus or to GL factors through the torus. So we can not worry about this. Yes.
So you said you don't have a proper while group. Do you have a while group point?
Yeah, that's while group point is the thing.
Yeah.
Like for instance.
But it hasn't been developed from that point of view. It still needs to be written.
Yeah, it's a.
So what reflections are not so clear here. Analogs of what reflections are not obvious at all.
Right.
Yeah,
there should be something like while group weight in there.
Absolutely, yes.
Yeah, you can sort of imitate some things, but
it's not
tricky. Yeah.
It's in fact developing an effective, workable theory like that is key to moving the subject forward, I think.
Yeah, so I also should have mentioned that the talk I'm giving now is some sort of progress report. So it's still in motion. So what I'm talking about is there's still a lot to do. So I'm going to mention some questions that are still open and a lot of theory to develop. But I'm just going to report on what is already known, and then I'll switch to open subjects. Okay, so fundamental group, homomorphism from fundamental group factors through the torus. We can start with some representations of the torus. We can also ask that it's like this honest representation with respect to the map from the fundamental group. Let's call this representation lambda. Then inflate it to the barrel. And then we want to do some sort of induction, but induction is much nicer in the context of algebras. So we will do this standard trick, and instead of looking at comodules over Hopf algebra, let's look at modules over the distribution algebra. So we can introduce the distribution algebra. Should have probably given definition before, but still, so the definition is absolutely as before. It's some co-limit of those finite things. So you take k of g, quotient by the some power of augmentation ideal, take the dual, take the union, has a Hopf algebra structure, and every G representation has the action of this algebra. And then you can ask yourself whenever what is the condition for your representation to integrate, to be integrable from the distributions to the actual group. There is some answer given by Siddharth, but basically, so you want to start with this representation lambda and tensor over distributions on B with distributions on G, L of X. And that's going to give you some sort of generalized Verma module. So let's call this M of lambda. And there is also some Poincare-Berghoff-Witt theorem that you can do that will tell you that as an n minus module over distributions on n minus, this is the same as distributions on n minus tensor lambda. So we know the size of this thing. We can do some computation with it. It's a pretty tangible object. And this object, it has this, we can look at it equivariantly with respect to this torus. And then if we have some sort of ordering on weights, on representations of the torus, then we can do some highest weight theory here. So if we know that lambda is in some sense the highest representation of the torus that appears, then this M lambda, admits the maximal quotient, the minimal quotient, so the quotient by maximal submodule. And this will be some simple module, and Siddharth proves, so the theorem is actually that those L lambdas give you all simple modules. And I'm
finite dimensional.
All finite. So sorry, there is some integrability condition on lambda. So some condition on lambda to integrate to G. And once lambda satisfies this condition, those L lambdas with this condition. So it's basically some dominance condition. So lambdas with this condition are all simple representations of GL of X. And So how much time do I have? I'm sorry. So what?
5 minutes. But
I have 5 minutes. Oh my God. Okay. So yeah. So that's.
You need the epsilon, right?
Yeah. That's epsilon. Yes. So I want to. So sorry. But I really wanted to share one particular nice picture. So I wanted to talk about combinatorics of this weight for the torus. So the torus, if you remember, is the product of GL of Li's. So we need to determine what are representations of GL of Li with epsilon. And so that's what I kind of wanted to quickly talk about because there is a nice combinatorial picture there that I wanted to share. So let me quickly erase this and try to make most of my time.
Just to make it clear, so Tx has semi-simple representation theory.
Yes, so it will turn out to be the case, yes. So what happens is that, so now so it's enough to look at representations of GL of Li and prove that it's semi-simple. So it turned out that GL of Li is a group scheme is just the image under this fiber functor that we constructed before of the GL of X, let me call it like this, where X is an element, is this generating the tautological I-dimensional representation of GLI. So we can look at Verlinde P of GLI, the semi-simplification of tiltings for GLI. We can look at this tautological representation, and there is a fiber functor F to Verlinde P here, and so this turns out to be precisely the image of this F, of this GL of X. And so as a reconstruction theorem, we get that representations of GL of Li with epsilon in Verlinde P is, as a category, it's just equivalent to this Verlinde P of GLI. Okay? And it's a semi-simple category. And so I wanted to, well, I really don't have time for this, I'm really sorry. So, but I wanted to just give you some combinatorial account on what the objects here look like.
So technically, you have to stop at 3:20, but then we can ask you a question. What is the combinatorial?
Thank you. Very nice question, Pavel. Thank you so much for it.
So why don't I ask it?
So recall that there was some condition on highest weight. So, oh, sorry. There is a Verlinde P of GLI, right? So it has this simple modules V lambda with the conditions that lambda plus rho theta less than P. And so how we can think about this? So lambdas, so if we were in the situation where it's SLI, then the last, so sort of lambda here is an I tuple of numbers of integers. In the case of SL, you were only allowed like positive numbers, and then it would look like some Young diagram for lambda would look like that it, so this is a condition lambda 1 minus lambda I less than or equal than P minus I. And so this would look like some box with the size I and P minus I. And for representation of GL, you can also add the same integer to every row. So you kind of have a diagram in the box plus some determinant representation, the tensor, some invertible thing. So that's your picture. And so, I mean, that's a simple object. So, sorry, yeah. Not true for GL. So for GL, you have finitely many kind of diagrams in the box, but then you're allowed to tensor it with invertible determinant representation. So you're allowed shifts by integers. So it's like finitely many up to invertible object. So I wanted to kind of share this, as I said, nice combinatorial way of thinking about this. So, you know, if we were just working with representations of GLI, let's just look at the classical picture, maybe even in characteristic 0. And we have this V lambdas, just lambdas are non-increasing. And so one way to decode those is to shift lambda by some row, by some sort of row. So you can start with some number A1, which is lambda 1, A2, which is lambda 2 minus 1, and so on, AI, which is lambda I minus I plus 1. And now they are strictly decreasing. And you can think about those as some points on the line.
We don't see it.
This is below the line.
Yeah, we can see it.
Oh, yes. Maybe here is OK. Let me draw this line. So you can think about those as just like fermionic points on the line. They are not allowed to be in the same place. And you can decode those highest weights. And there is some categorical meaning for this by i's wedge power of some infinite dimensional thing. So you can kind of sort of think about C infinity as being spanned by VAs. And then you can look at VA1, VA2, and so on, using these AIs. And then you can encode your highest weights by some
semi-infinite weight. Semi-infinite.
No, it's just the i's power of the infinite thing. And that's, you might have seen this. So this is like some categorical type A action of SL infinity, and it gives you this picture. And I wanted to say what sort of picture you get for Verlinde P of GLI. So,
sorry, can I interrupt?
Yes.
So maybe we should stop here because
yes.
there are some people that need to hang the posters, and then
yes.
we can ask you questions in.
Absolutely, yes. So people who don't want to hear this and who need to submit. Thank you.